Hello everyone, I'm Kazi Asifuzzaman and I welcome you to the presentation. Today we are presenting a work that we have done on analyzing high bandwidth memory HBM for real-time systems. The title of the paper is Demystifying the Characteristics of High Bandwidth Memory for Real-Time Systems, and this is a work that has been done in collaboration between Barcelona Supercomputing Center in Spain and McMaster University, Canada. Let's get a brief overview on real-time systems. Real-time systems are special computing platforms that requires functional guarantees with timing correctness. That is, certain tasks must be completed before a specific deadline. Failure to meet this requirement may have fatal consequences. Some of the examples of such systems are flight management system, cruise control, etc. To achieve timing correctness, we have to ensure that software functionalities run timely, and for that we need to derive time bounds per task, and predictable hardware systems facilitates such analysis. Advanced software functionalities such as autonomous operations require unprecedented memory and computing performance. This is mainly due to the enormous amount of data that is coming through the sensors, which are to be processed on high rates. Computing performance is being subsidized by GPU and accelerators, and memory performance is struggling with the traditional technologies that are being implemented. HBM can come as a viable alternative to provide average performance that is needed for these advanced software functionalities. However, HBM memories needs to be analyzed for the timing predictability properties before incorporating in real-time systems. In this study, we explore HBM structure and timing from a real-time perspective. We also investigate the features of HBM that can be exploited to increase isolation or reduce worst-case latency for real-time systems. For the empirical comparison of HBM and DDR4, we use state-of-the-art cycle-accurate memory simulators, and we also implement a timing simulation model to analyze the HBM features that are not being implemented in the memory simulators yet. Continuing on, we have already discussed real-time systems and the possibility to incorporate HBM in the domain. Now we continue with a brief overview on the DRAM timing, details on HBM structures and features, and how these benefit real-time systems. Then we present the results of our evaluation and conclusions of the study. It is worth to mention that DRAM and HBM both uses DRAM cells as their core memory array. In the picture on the left, you have a DRAM diagram, which can be seen as a planar layout, and on the right you have a HBM diagram, which can be seen as a 3D layout. But both of these technologies, they use DRAM banks to save the data. On the right, we have a DRAM timing diagram. So the timing diagram specifies the delay between two stages of memory operation. For example, in bank 0, if you have an activation, you have to wait a row to column delay or TRCD time before issuing a CAS command with read or write. Similarly, if you have a write on a bank and then you have an incoming read on another bank, then you also have to satisfy a write to read delay in this case. The table specifies the values for these delays. So this table shows the numbers that we have used in our study to model HBM and DDR4 for our experiments. Here we highlight the HBM features that are distinctive from DRAM or any traditional memory systems. HBM has a 1024-bit wide connection with the processing unit. This is made possible by putting the processing unit and the HBM stacks on the same silicon interposer. HBM can have multiple stacks connected to the processing unit, and each of these stacks can have 4 or 8 layers, and each layer, each core die can accommodate 2 channels. These channels are independent. These channels are then further organized in banks. Each of the banks are 128-bit wide. So these are, if you look on the right, there are two blue highlighters which highlights a half bank, a B0 half bank on the left and B0 half bank on the right. So both of these banks produce 64-bit data, which constitutes 128-bit data from each bank. And then one channel is further divided into a pseudo channel. The pseudo channel is constituted by the set of half banks, and this is a distinctive feature in HBM2, um, and which produces 32 byte data in each axis. HBM further implements separate row and column pins. HBM also provides a shorter column-to-column delay than DDR4. Another feature of HBM is implicit precharge, which we would be discussing on the coming slides. And HBM can avoid the 4 active window constraint with pseudo channels. Isolation is a well-known technique to reduce contention among tasks in memory. It prevents interference from competing tasks to ensure a more deterministic execution time. HBM offers several degrees of isolation with its unique structure. It provides the opportunity to have isolation on stack level, channel, or bank level, and even some degree of isolation in pseudo channel and half bank level. Now let's see how HBM can be advantageous on bank partitioning. Under bank partitioning, for the common data bus width of 16-bit for DRAM and with the maximum burst length of 8, a 64-byte cache line size would require 4 accesses to serve the data. On the other hand, with pseudo channels in HBM, with a burst width of 64-bit and burst length of 4, it takes only 2 accesses to provide the same amount of data. Let's talk a little bit more about HBM features. HBM has a reduced cache latency in comparison to DDR4 DRAM. In this example, let's assume that we have 3 consecutive cache commands in different banks in the same bank group. So this is specified to be column-to-column delay, or TCCD, is specified to be 6 cycles for DRAM. And with this delay, the sequence finishes at 31st cycle. For the same sequence, since HBM provides a lower column-to-column delay, it's 2 cycles in case of within the same bank group. The same sequence finishes in 21 cycles. Another important feature of HBM is implicit precharge. Implicit precharge feature allows HBM to issue an activate command while another row is still active. So let's assume that we have a data burst on 31st cycle, and then we have another request to open a new row in the same bank. So we have to precharge the currently open row, and that arrives at cycle 37. But we have still pending ready commands in the 7 other banks, which delays the precharge command to 44th cycle. And then it has to suffer the row precharge timing, and it can finally issue the activate command on the 59th cycle, and the whole sequence finishes at 92 cycles. For HBM, you don't have to issue the precharge on the 37. It can directly issue the activate as long as the row cycle timing is satisfied. For the same sequence, in example, HBM completes 7 cycles earlier than DRAM. Another important feature of HBM is dual command bus. HBM employs dedicated pins for transmitting row commands and column commands. In the example, let's assume that we have 1 activation and 1 cache commands arriving at the same cycle for DRAM. Since DRAM shares the command bus between row commands and column commands, the cache commands needs to be delayed by 1 cycle, assuming that activation has a higher priority. For HBM, they can be issued at the same cycle. However, they still need to respect the DRAM timing constraints since they are imposed by the internal structure of the array. The other feature that HBM has is to avoid the large 4 active window constraint. For example, for DRAM, when you have 4 consecutive activations, then the fifth activation needs to wait until a certain time. This means that if the TFAW is configured to be 32 cycles, then the fifth activation can be issued on 33rd cycle. So this causes a delay from 52 cycle to 63 cycles in this sequence. For HBM, if we use pseudo channels, then there are no similar timing constraints which causes this delay. So by cleverly interleaving and accessing pseudo channels, we can issue activations without any such delays that is shown on the DRAM case. However, the HBM has an activation of 2 cycles, so this is one of the major drawbacks of HBM. And in this example, if we take into account the two cycle activation for HBM, both of the sequences for HBM and DRAM finishes at the same time. For the simulation infrastructure, we use the Maxim CPU simulator integrated with DRAM Sim3 as its off-chip memory. In particular, we model a single channel DDR4 with 1 rank and 8 banks, and for HBM we have 1 stack with 4 dies, each with 2 channels and each channel having 16 banks. Both HBM and DDR4 devices are running at the same frequency. For the benchmarks, we aim at modeling real-time applications with varying memory demands. We model control type applications with benchmarks from Embassy Autobench. We model payload applications by using a matrix multiplication kernel that we configure with different total memory footprints. We also use the bandwidth and latency micro benchmark from the ICCAD suite. The table lists the organizational parameters for the simulations conducted for this study. Please note that the simulators that are being used were built to measure performance-related studies, whereas these new HBM features are abstractly implemented in these simulators. So we implemented a C++ model for stressing these specific HBM features that are missing in the mainstream simulators. Here we present the results of our simulation. First, read requests. With this test, we quantified the number of read requests issued by HBM and DDR4 DRAM. We see a significant reduction in number of read requests issued by HBM. To be specific, 6.5 times reduction in MPC benchmarks and 8 times reduction in bandwidth benchmarks. The other remaining benchmarks, latency and matrix multiplication, cannot fully exploit the large request size of 512 bytes of HBM due to the cache conflicts. We also measured the worst latency captured for each of the benchmarks under study. The worst latency signifies the single request that took the longest time to serve. The worst case latency with HBM ranges from 291 to 353 cycles, and the worst case latency with DRAM is in the range of 415 to 480 cycles. HBM also shows significant improvement with execution cycles. Non-memory intensive benchmarks Embassy shows 12% improvement on performance. And memory intensive benchmarks such as bandwidth benchmarks shows up to four times of improvement in comparison to DDR4. And we can achieve comparable performance with latency and matrix multiplication benchmarks. We also measure the total off-chip memory time for HBM and DDR4. The total off-chip memory time is reduced by 5 times for Embassy benchmarks, and for the remaining benchmarks, it ranges between 6 times to 9 times reduction for HBM. In previous experiments, we assumed that a request to HBM is interleaved across all the channels to utilize the wide interface of 1024 bits. This is a common approach in high-performance systems to increase the off-chip memory bandwidth. However, a common approach in real-time systems is to enforce isolation by partitioning the off-chip memory among requesters to minimize memory interference. We evaluate the bandwidth loss incurred if the application accesses a single HBM channel compared to being interleaved across all the channels. We see that achieving isolation comes at an expense of a bandwidth degradation. For MBC benchmarks, this degradation ranges from 15% to 45%, and for bandwidth-intensive synthetic benchmarks, this ranges from 67% to 87%. Please note the bandwidth latency trade-off is a use case dependent and hence depends on the running of a set of the applications. Here we explain the synthetic model that has been developed and the tests that we ran for stressing particular features of HBM. So the memory simulators such as DRAM Sim3 were primarily developed targeting to evaluate performance of a system. Therefore, some of the features such as pseudo channels were abstractly implemented in these simulators. Abstract implementation of features is okay for performance studies, but for real-time systems, it requires to accurately model the features to get a more deterministic evaluation of the execution time. To meet that end, we developed a C++ model to capture newer HBM features missing in the simulator. And we developed 4 synthetic tests to stress dual command, bank partitioning, reduced column-to-column delay, and TFAW features of HBM as we explained earlier. The test dual command issues a series of CAS commands with an interfering series of activation commands to another bank. Partition assigns a single bank to the emulated core running the trace. Column-to-column delay is a test of open requests targeting the same row, and TFAW issues closed row requests to different banks issuing consecutive activation commands. The results show dual command and reduced TCCD features notably contribute to bandwidth improvement. Dual command feature of HBM can issue activate and CAS commands in parallel, effectively eliminating bus conflicts and therefore suffering minimum stall cycles, improving the sustained bandwidth. Reduced TCCD also allows HBM to issue consecutive CAS commands in shorter time, therefore improving bandwidth as well. The bank partition feature enables HBM to provide 32 bytes per single access, therefore filling a 64 byte cache line in just 2 accesses. Feature TFAW refers to the timing requirement to open maximum 4 active windows in a certain time. Since HBM improves this requirement, we see that it achieves increased bandwidth and reduced execution time with respect to DRAM. On the concluding notes, this is the first study analyzing HBM for real-time systems. We identify HBM features and structures that could be exploited for the benefit of real-time systems. We also identify HBM properties that contributes to achieve a better worst-case latency, which is important for real-time systems. HBM also performs significantly better in all other performance metrics such as execution time and off-chip memory time. This work provides a solid foundation for future works to explore HBM's use in the real-time domain. This work has been supported by the Spanish Ministry of Science and Innovation, the European Union's Horizon 2020 Framework Program, and the European Research Council, along with Natural Sciences and Engineering Research Council of Canada. Thank you very much for your time and attention on the presentation. We would like to take the opportunity to thank the organizers of International Conference on Computer-Aided Design, or ICCAD, for giving us an opportunity to present this work. Thank you.